Hello and welcome to my new video. This time I will be talking about small molecules. How do we know that it's H2O or NH3 and not H4O or NH2? There are pretty simple rules how atoms should be composed to molecules. Second point of the video is the steric arrangement of these atoms. In chemistry, the steric shape of a molecule is pretty important. Again, as you will see, there are simple rules for this steric shape. These rules are becoming somewhat more complicated for higher elements, and therefore I will restrict this video to the first 10 elements. These are pretty important elements anyway. I will talk about other groups of elements in later videos, so here it's only about the first 10. Okay, what are the first 10 elements? To find out about this, we have to shortly go back and look at the composition of an atom. An atom consists of a nucleus, which contains the positively charged protons and some neutrons as well, and it consists of an envelope, which contains the negatively charged electrons. The number of protons is called the atomic number, and this determines the nature of an element. So the elements differ in their atomic numbers, that means in their number of protons in the nucleus. And this number of protons also determines the number of electrons in the envelope, at least in the neutral atom, and this in turn determines the chemical properties of a given element. So the first 10 elements differ in their atomic numbers, in their numbers of protons in the nucleus. We start with hydrogen, with 1 proton in the nucleus, atomic number of 1. Go on with helium, 2 protons in the nucleus, and so on. And we end with neon, which has 10 protons in the nucleus, atomic number of 10. These are the first 10 elements, and we can simply add the chemical symbol to them. I've already talked about how electrons are arranged in the envelopes of atoms, so therefore I will only give a very short summary here. They are not present as conventional particles, but wave-particle duality is applying to them, and therefore they are rather forming standing waves of the probability to encounter the electron at a given place. And there are different waves which can be formed. These are called orbitals. So here I have depicted the orbitals which are important for the first 10 elements. It's the 1s orbital, the 2s, and then 3 different kind of p orbitals. Each of these orbitals can be occupied by 2 electrons, and one important point about these orbitals is that they have different energies. So the 1s orbital has the lowest amount of energy, the 2s orbital has a higher amount of energy, and the highest amount of energy refers to the p orbitals. They all have the same amount of energy. And now the orbitals are occupied by electrons with increasing energy. So first the orbital of lowest energy is occupied, and then all the other orbitals are occupied. These orbitals can be combined into shells, and here we are talking only about 2 shells with the first 10 elements. First, the first shell, this only comprises the 1s orbital, and the 2s and the 2p orbitals, can be combined in the second shell. As I just said before, the electrons from the various elements are filled up in these shells and in these orbitals with increasing energy. So first the 1s orbital is filled, therefore the electron of hydrogen and of helium are located in the 1s orbital. Then the 2s orbital is filled, so the electrons from lithium and beryllium are filled in the 2s orbital, and so on. Then the other elements are filling up the 2p orbitals. If we use 1 dot for every electron, then we can visualize the numbers of electrons in the outer shells, like in this picture here. So hydrogen has 1 electron in its outer shell, therefore there's 1 dot. Helium has 2 electrons in its outer shell, therefore there are 2 dots. In the case of lithium, we are looking only at the second shell now, so there's only 1 dot, because in the second shell there's only 1 electron. Lithium has 3 electrons, but the first and the second of these 3 electrons are located in the 1s orbital, and this is not part of the outer shell in the case of lithium. In a similar way, beryllium has 2 electrons, boron has 3 electrons, and so on. One important point is also that we are filling each orbital first with a single electron, and then we are adding a second electron to the orbital. So carbon has 4 single electrons and not, for example, 2 double electrons. One of the most important principles in chemistry, or maybe even the most important principle in chemistry, is the tendency of elements to fill up, to either fill up their outer shells or to completely empty them. So they try to either get rid of all their electrons in the outer shells or to fill them completely up to have a configuration like neon. And this principle is called the octet rule, because a neon has 8 electrons in its outer shell, and this would be something like a perfect configuration of electrons. So most chemical reactions are driven by this principle, and we can distribute the elements in different groups according to the strategy they have to fulfill this principle. So let's have a look at the various groups in this picture here. First of all, there's group 4. Let's start with group 4. These are the noble gases. They already have a completely filled up outer shell, and so they are perfect, and so therefore they don't react at all. They don't want to lose electrons, and they don't want to gain electrons. Therefore, they are perfect. Group 1 is pretty easy as well. Elements from group 1 have 1 or several electrons too many in their outer shells. They simply have to get rid of these electrons, and then they are becoming positively charged ions. The electrons are negatively charged and the nucleus is positively charged, and when they lose an electron, like lithium should lose 1 electron, then it would have 1 positive remaining charge. Beryllium should lose 2 electrons to empty its outer shell, and then it has 2 positive charges remaining. And the same is true for boron, which has to lose 3 electrons, and then it will be a threefold triple positively charged ion. The strategy for group 3 is also pretty straightforward, like oxygen or fluorine. They have 1 or 2 electrons too little in their outer shells, and they just have to gain these electrons from some other elements or from other stuff, and then they are negatively charged because then they have surplus electrons in their outer shell. So oxygen, if it is gaining 2 electrons, then its outer shell is filled. It has then 8 electrons in its outer shell, and it has 2 surplus negative charges. And fluorine, it has only to gain 1 electron in addition, and then it will have 1 negative charge as an ion, a negatively charged ion. So the remaining group 2, for them it's not possible to simply skip or gain electrons because they would be charged too strongly. Apart from either losing electrons or gaining electrons directly, there's still another strategy which atoms can go to fill up their outer shells, and this strategy is done by group 2, and this consists of constructing molecular orbitals, of sharing electrons with other atoms, and then these shared electrons, they will belong to the shells of both atoms. In my last video about chemistry, I talked about this combination of atomic orbitals into molecular orbitals in a bit in more detail. So here I will do this only very shortly. Let's have a look at these 2 hydrogen atoms. Each of them has 1 electron, and each electron is present in the 1s orbital. And these 1s orbitals can be combined together to form a molecular sigma orbital. And this pair of electrons then in the sigma orbital can be symbolized by a dash instead of 2 dots. And this dash is also meaning in this case these 2 atoms now are connected and are forming a molecule consisting of 2 hydrogen atoms. Okay, now, and these 2 electrons in this molecular orbital, they are belonging to both atoms. So each of these hydrogen atoms has now 2 electrons in its outer shell, and that is the thing they wanted. They want to have 2 electrons in the outer shell, and by forming this molecular orbital, they have obtained this. How will hydrogen react with the other elements from the first 10 elements I've shown here? We will start by looking at carbon in a bit more detail. So carbon has 4 electrons in its outer shell and it wants to have 8 electrons in its outer shell, and hydrogen has each 1 electron in its outer shell, and they are reacting simply by forming 4 molecular orbitals. Remember that 1 molecular orbital can be formed from 2 atomic orbitals, each occupied by a single electron, which is perfect in this case here. And now each hydrogen atom has 2 electrons in its outer shell, like it wants, and each carbon atom has 8 electrons in its outer shell, because the electrons from the molecular orbitals belong to both atoms, to the shells of both atoms. Now, if we go back to the other elements and look how they can react with hydrogen, or how they can form molecules together with hydrogen, we will skip the boron here because boron is a bit more complicated case. I will talk about boron in a later video, but we will talk about all the other elements here. And as I have shown you for carbon, the number of hydrogen atoms which can be bound and which have to be bound to these atoms um, refers to the number of single electrons in the atomic orbitals of these elements. So nitrogen has 3 single electrons in its outer shells and therefore it can form 3 bonds with hydrogen. Oxygen has 2, so it can form 2 bonds with hydrogen. And fluorine finally has 1 single electron, therefore it can form 1 single bond with hydrogen. And this number of single bonds which can be formed by each element, this is called the valence of this atom, or of this element. And this is a very important feature in chemistry for the individual elements. Except for the fluorine compound, all other compounds here are pretty common compounds. So the molecule with 1 carbon atom and 4 hydrogen atoms is called methane. The molecule with 1 nitrogen atom and 3 hydrogen atom is called ammonia. And the compound with 1 oxygen atom and 2 hydrogen atoms, this is called water. It is time to summarize the rules determining how atoms can be composed together into molecules. Interactions between atoms are depending on their outer shells of electrons. The most important way for forming bonds between atoms is the combination of 2 orbitals from different atoms, both with a single electron, into a common molecular orbital. This way, the number of single electrons in the outer shell determines the number of bonds a given atom can establish, its valence. As I have shown you, it is pretty easy to determine this number. Once you know this valence, you can predict, at least in many cases, which molecules can be formed by 2 or more elements, and you can test whether a given chemical formula is correct. The simple picture becomes somewhat complicated by 2 things. Atoms can establish not only single bonds between them, but also double or even triple bonds. And second, in chemistry, we also want to know about the precise steric arrangement of a molecule. I will talk about these points in the second part of the video. After we have looked how many hydrogen atoms can be bound by each of the several elements, now let's have a look at the steric arrangement of these atoms in these molecules. And this means primarily let's have a look at the angle between 2 hydrogen atoms in this case. And as you can see here, the angle between these hydrogen atoms is between 109 degrees and 104 degrees. How can we obtain such angles? Apparently not by the conventional arrangement of orbitals, as I have introduced it to you in this video and in other videos. This arrangement of 2s and p orbitals, because these p orbitals, they have angles of 90 degrees towards each other and not of 109 degrees, so have smaller angles. So we have to find an alternative to explain the formation of these angles. This alternative can be found when the orbitals of the second shell, so the 2s orbital and the 2p orbitals, are mixed up with each other and are used to form new, completely different orbitals, so-called hybrid orbitals. And since there's one s and three p orbitals for this hybridization, this is called an sp3 hybridization. And these sp3 hybrid orbitals, they are arranged in a tetraedric way around the central atom, and and in this case the tetraedric angle is 109 degrees, and this is fits perfectly to the angle of the methane molecule. It also explains the angles of the other molecules of ammonia and of water if we assume that the lonely pair of electrons, which is also present in the shells of these molecules, or two lonely pairs of electrons, take a bit more space than the bound hydrogen atoms. And then therefore the angle of 109 degrees for methane is a little bit reduced to 107 and 104 degrees in the case of ammonia and water. Let's look at the other elements, and let's start with oxygen. Oxygen has a valence of 2. It has two single electrons in its outer shell. You can see this particularly well when you replace the dots of electron pairs with dashes. Then you see there are two pairs of electrons in the outer shell and two single electrons. And as I've already shown you, oxygen can form two bonds with hydrogen. This would be then water divisor. But oxygen can also form double bonds. And an example is the molecule which is formed by two oxygen molecules. So this is forming a double bond. And if you then have a closer look at it, you see each of these oxygen atoms now has 8 electrons in its outer shell, because the electrons from the bond belong to both oxygen atoms. And so that's the perfect arrangement for these oxygen atoms. Oxygen also can form double bonds with other elements. I've just symbolized these elements here as R. But it can also form single bonds with other elements, and for example form another single bond with hydrogen. This is a very common case, and these molecules are then called hydroxides, or when they are bound to carbon, they are called alcohols. Now let's go back to carbon, and let's have a look at the compounds this element can form together with oxygen. As I've told you before, carbon has a valence of 4, so it can form 4 single bonds. And if we think we replace one hydrogen from this methane with one hydroxy group, then we come up with the simplest alcohol with methanol. Oxygen has a valence of 2, so it can form double bonds. And if we just form a double bond here, we come up with the formaldehyde. If we go further and integrate another hydroxy group into this molecule, then we come up with formic acid. And the final compound in this row is carbon dioxide, where we have two double bonds to two oxygen atoms. When you look at the angle between the binding partners for this carbon atom, you see that the angle is not always 109 degrees. In the case of the carbon atom forming one double bond, the angle is 120 degrees. And in the case when the carbon atom is forming two double bonds, the angle is 180 degrees. And this angle can no longer be explained by an sp3 hybridization. And therefore, we have to find other forms of hybridization for explaining this angle. So here I still summarize the sp3 hybridization. So all the orbitals from the outer shell are combined with each other to forming 4 new sp3 orbitals, which are arranged by an angle of 109 degrees. Other hybridizations are possible when we exclude one or two p orbitals from the hybridization. Then, in the first case, when excluding one p orbital, we would have an sp2 hybridization. So now one s orbital and two p orbitals are mixed up with each other and form 3 completely new sp2 orbitals. And these are arranged in one plane. This is very important that they are arranged in one plane and they are yeah 120 degrees apart from each other. So the angle between them is now 120 degrees, precisely as we saw it in the case of formaldehyde and formic acid. And if we have, and the 2p orbital which is remaining can then be used for forming this double bond. And in the case of two double bonds, we have to exclude two p orbitals from the hybridization because we need these two p orbitals to form the two double bonds. And so we have an sp hybridization between one s and one p orbital. And this is forming two sp orbitals. And these are now building an angle of 180 degrees, precisely as we see it in the case of carbon dioxide. And two p orbitals are remaining for building up the new two double bonds. To repeat this for our molecules formed with carbon, so the methanol has an angle of 109 degrees, and this is an sp3 hybridization. Formaldehyde and formic acid have angles of about 120 degrees, so they have sp2 hybridization, and the carbon dioxide has an angle of 180 degrees between the two oxygen molecules, and this refers to an sp hybridization. Now let's have a look at formaldehyde. How is this molecule constructed precisely? For a start, I skipped the p orbitals. So here you see only the three sp2 hybrid orbitals from carbon to hydrogen atoms and to the oxygen atom. They are within one plane, though this is completely planar, this molecule, and they are all arranged by 120 degrees. And then you also see the two pair of electrons which are belonging to the oxygen atom, which I'm representing here as little spheres. Okay, now just to show you that this molecule is planar, I will just turn it a bit around, and now I can add the p orbitals to it, which are arranged perpendicular to the plane of this molecule. And by combining these two p orbitals from the carbon and from the oxygen atom, we can form the p molecular orbitals, which are arranged like this. This would be an example where both partners, the carbon and the oxygen atom, have sp2 hybridization. Now let's take a look at carbon dioxide, where one partner, the carbon atom, has an sp hybridization for its orbitals, and the other two molecular partners have an sp2 hybridization, the oxygen atoms. So the carbon has only two sp orbitals, which are differing by angle of 180 degrees, and then two remaining p orbitals, which are perpendicular to this axis. And the oxygen atoms, they have sp2 hybridization. That means they have three sp2 orbitals, which are arranged in planes in each case. And I have symbolized the free pairs of electrons as spheres as before. And you can see again they have one p orbital. Each oxygen atom has one p orbital, which is arranged perpendicular to the plane of its sp2 hybridization. Now, if we look at the double bonds which can be formed in this case, you have to be aware that the two p orbitals from the carbon, one can react with the oxygen atom above, and the other one can react with the oxygen atom below. And therefore, we will have two pairs of p orbitals connecting the carbon atom on the one hand to the oxygen atom above, and on the other hand on the oxygen atom below. Carbon dioxide is an example where the sp hybridization of one atom, of the central carbon atom, is leading to two double bonds with two different atoms, with the two different oxygen atoms in this case. Here, as the last example, I want to present you a molecule where two atoms have the same hybridization, both have sp hybridization, and then a triple bond is formed between these two atoms. As you can see here, again, the molecule is completely linear, so it's an angle of 180 degrees in all cases, and the p orbitals are positioned perpendicular to this axis, and they can interact. Both p orbitals can interact with each other. So we have three bonds in total between these two atoms, between the carbon atom and the nitrogen atom, which we took in this case. The compound which is shown here is hydrogen cyanide. It's a very toxic compound. And if you still take a short look at the valence formula of this molecule, and if you count the pairs of electrons and the electrons in the shells of each of the atoms, we will do this as a last kind of exercise. Let's start with the hydrogen. Hydrogen has one bond with two electrons, so it has two electrons in its outer shells, as it has to have. Carbon has three bonds with two electrons each, so it has eight electrons in its outer shell, as it should have. And the nitrogen has three bonds and one lonely pair of electrons, so again it has eight electrons in its outer shell, like it should be. At the end of this video, let me shortly summarize the steric rules I have shown to you before. So we can distinguish three different cases. First case is there are only single bonds in the molecules. Then we have sp3 hybridization for the central atom. So the orbitals for the central atom are four sp3 orbitals, which are arranged in a tetraedric way and with an angle of 109 degrees between these orbitals. And those are the bonds which are formed then by this central atom. In the case when you have one double bond in your molecule, then you have an sp2 hybridization. That means the central atom has three orbitals, three sp2 orbitals, which are arranged in one plane and which are apart from each other by an angle of 120 degrees. And so are the bonds which are then formed. And the remaining lonely p orbital is then used for forming the double bond. In the case you have a triple bond or you have two adjacent double bonds, then the central atom has an sp hybridization. That means there are two orbitals which are apart from each other by 180 degrees, so are completely linear, which are sp hybridized. And you have two remaining p orbitals, and these two remaining p orbitals can be either used to form a triple bond or to form two adjacent double bonds. So these are the only three cases which can occur, at least under usual conditions. So I hope you watched until this point. Now you can set up a single molecule and predict its steric shape. It's not rocket science, as you see. Of course, there's more to it. There are larger elements with more complicated outer shells. There are other mechanisms how atoms can interact with each other than by combining two single electrons. And last not least, our tacit assumption that molecular orbitals, bonds, are only formed by two interacting atoms is not always true. I will talk about these things in later videos, so in case you want to learn more about molecules, stay tuned.